Hello, I'm going to be going over my chemist in a spotlight today, and the chemist that I chose is Carolyn Bertozzi. She's an American chemist, and she got her undergraduate degree at Harvard and went on to get her doctorate at UC Berkeley. She has been awarded four main or commonly known awards, including the Wolf Prize in Chemistry, the Lemonson MIT, the MacArthur Fellowship, and she is also one of the three Nobel Prize winners for 2022. And the research that she won the Nobel Prize for is what I'm going to be covering today. So her main background behind the science for the why she won the Nobel Prize is due to bioorthogonal chemistry. So what bioorthogonal chemistry does is kind of creates a bridge between chemistry and biology. And what's cool about it is that researchers before her, the other two researchers that also won the Nobel Prize along with her, created what's known as like click chemistry. It's also heard as click chemistry, and it uses copper catalyzed. It's copper catalyzed, and she wanted to use it in a biological sense. And research was done actually in one of her articles that I'm going to be like referencing throughout the video, called A Comparative Study of Bioorthogonal Reactions with the ZIDs, where they found that the copper catalyzed reaction was efficient with detecting the azids. However, in live cells, it was not efficient. That was due to the copper being toxic to the cells. So she wanted to find a way around that, or find a better way to to use the mechanism of how the reactions just work with. It's kind of like a way of green chemistry as well, because the reactions just work. They have a very high yield, and they don't produce many byproducts. So she wanted to have a way to do that, but in a biological setting, so to remove the copper. And in doing so, she created bioorthogonal chemistry. And basically, what that is it's like a tool that aids in studying glycobiology and underlying diseases, which is what her research mainly does. And some of her articles go over researching into cancer, tuberculosis, recently COVID-19, and inflammation. So it allows, bioorthogonal chemistry allows for the modification of a cell, but however, it won't hinder or affect the cell's original way that it was living or behaving in the body or the system that it was in. So basically, for like a visual example, I have this exomarker, and it's kind of like, this is the exomarker, which is the cell itself, and we're tagging it with this lid. So the lid doesn't affect the fact that this exomarker stayed like the white right here and the red right here. It's just now a part of this compound. So that's basically kind of a little visual representation of what her research is about. It's about getting molecules and tagging them and probing them, and the probe would be kind of like adding just another thing on here. So we have our structure with tag on it, and we're going to probe it so that when it does go in the body, we can follow this part through fluorescent visualization or just other detective methods. I'm so sorry, excuse me. With other methods. And this part is what would be visualized. So we can see the cell, and you can also see this part around it as it goes through the body. So this is what's this is what's aiding in being able to visualize the cell that was tagged and probed. Okay, so one of her research articles is called A Comparative Study of Bioorthogonal Reactions with the ZIDs. And in that article, specifically, it was introducing or focused on the background of introducing azids into target molecules, and that could have been done metabolically or through a chemical modification. So in that article, they found or they were using highly selective reactions to target the azids. So we have the Schrodinger, the copper catalyzed, and we also had the strain one. So there's a 3,2 cycloaddition strain, and there's also just a strain that's been done with other stuff as well, like amines and stuff like that. And in this study, they found, or it was solidified, that the Schrodinger ligation and the cycloaddition strain, so this is what happens with this one is that since there's so much strain on the molecule, it forms another cycle with the nitrogen in the cycle specifically. And so these two were found to work with or on live cells, while this one was found to be efficient on other aspects of chemistry, but not on live cells. So from there, I'm going to go in order a little bit and touch over some articles that mention that she's published that mention these reactions. Mainly the Schrodinger reaction and then some other reactions. The copper catalyzed one, since she focuses on biological studies, she tends to shy away from using the copper catalyst since it is toxic on the live cells that she's trying to target and determine and collect the pathways for. So going into the first one, it was called the imaging cell surface glycans with bioorthogonal chemical reporters, and this was published in 2007, and it focuses on using azids and ketones. And so what I'm going to do now is throughout the video, I'm going to also be referencing another article that she published, which is called Bioorthogonal Chemistry, a Covalent Strategy for the Study of Biological Systems. And in this article, she breaks down the key components of what's happening in the reactions, or just like an overview of how it looks. So for the azid and ketone part that's happening, or that they were using for the imaging cell surface glycans article, in that article, I'm going to write and talk. So in that article, they were basically trying to find an efficient way to target the cell itself. And two types. We have a group here, and this and in this reaction, it works best. This is not an oxygen, and this is not an oxygen. These are the probes that I was mentioning earlier. This is a molecular probe. This is a molecular probe, and this is the target molecule. So we have our molecule that we want. Target molecule. So in this reaction, basically this is the ketone one. So we're we're kind of pushing, this is what all of the reactions do. They work quick and they are efficient. And what happens is the nitrogen group kind of just pushes itself onto the part that has the target molecule on it. So you're left with the structure with the nitrogen group, the target molecule, and the probe. So we're able to track it because we added these two components onto our target molecule from the beginning. So the problem with the original way that it normally happens, because people have been able to attach fluorescents onto cells for a while. However, it was attaching very large molecules onto the cell itself, and it was causing like the structural perturbations in the cell, in the compound, and it wasn't that versatile either. You can only use it on like specific compounds, and it couldn't be applied to lipids, glycans, and nucleic acids. Whereas this reaction happens very quickly, very efficiently, and as well as you're able to, since it's such a small molecule in comparison to what was previously used as fluorescents, or what is still being using as fluorescents, this one is able to attach to those glycans, the nucleic acids, lipids, and stuff like that. So going into to finish off this research, so what they did or noticed was basically when they were checking the checking the visualization part of everything, they just put it and checked that you're able to see that something has been probed and something has been on there, and they had the cell itself, and then you can see the cell was kind of protected with this layer that I'm coloring in red, but to them it was the fluorescent layer. So it worked well, and it kind of just looked like that. You had the cell right here, and then you had the fluorescent coating around it. Okay, so the next article that I'm going to talk about is called From Mechanisms to Mouse, A Tale of Two Bioorthogonal Reactions. And the main reactions that they focused on in this article was the Schrodinger ligation and reduction reactions. So the first one that I'm drawing is just an overview of the ligation one. We have our nitrogen groups. So the nitrogen chain here is connected to the biological target, and what they did was reacted it with this structure. And then there was also this group here, 2 and 1, 2. Then we have our ketone group here, and this. So it's kind of cool. So we have this group right here. This is the molecular probe. So this is the molecular probe. Okay, so we have our nitrogen chain group here connected to the biological target, and we have our other group here carrying the molecular probe. So what's going to happen in this reaction is that water is going to be added, and this methanol is going to leave, as well as N2 group, and it's going to connect these two together. So the end product that it's going to look like is going to have both the biological target and the probe on the same structure. And a common theme in all of her research is just solidifying if and how efficient these reactions are. So as this was just coming into the scientific industry, everything needed to be backed up. So her few articles, like her articles from the past, like in 2006, 2014, they mainly focus on like solidifying how well these reactions work, how efficient they are. And having a biological target and a probe in two separate compounds and just quickly reacting them so that we can get them on the same compound and then follow this compound and track its pathway, its metabolic pathway, or however it's working in the body. So this is the ligation portion of that. There's also a Schrodinger reduction, and that happens with this same group right here, but I'm going to draw it here, or I'll use a different color so you can see a little bit better. So here, there we go. We have this group, and now the green spot is our biological target, and our X is cleavable, like it's cleavable linker. So here we're still gonna have this group, the pH2 group, and what's gonna happen is we're gonna lose this nitrogens, and we're gonna be able to link these two together. So we're gonna have this here, and we have our nitrogen group here. Just looks like this. And then this is the X. And this is still attached to the biological marker target, the biological target. So this was the reduction way, and this is the ligation way. They still work towards the same goal of having two separate compounds, and then when they come together, it has the final product has the target, the biological target, and the molecular probe. So I'm going to erase this now. Okay. Now for the next few studies I'm going to talk about, I'm not really going to draw anything. I'm just going to do like a kind of like what she went over, and because they were new stuff at the time, and it wasn't really solidifying anything. It was more like, now that we know we have this bioorthogonal chemistry and we have these reactions that work very quickly and very effectively, how can we, or what can we do to create new reactions that might be able to help in a different sense with the same background. So one of those things, I have my other, the school's computer right here, so I'm referencing my notes if I'm looking this way. So another publication that she did is called bioorthogonal quadracyclane ligation, and in there she was basically trying to create a new, or have a new addition to the bioorthogonal chemistry. So on top of the Schrodinger ligation, the strain promoted cycle addition, and the as well as the like copper ligand one, also known as like the click chemistry, the one that just happens. All of these just happened, but that one is like mainly what sparked everything, was the copper one at first. She's trying to, in this article, is add another reaction that works in the same sense. So the reaction, the quadracyclane ligation reaction, is able to work because of the strain that's happening between the hydrocarbons and the nickel bis diethylene that they're adding into the environment. And so at the end of the study, they were able to find that it was comparable to other quick azide reactions, like similar to the Schrodinger ligation. They were able to use that as well, and they compared the two and found that the results were the same, that it was able to work in a living cell and still happened quickly and effectively. So It was also found that the quadricyclane is compatible with strain-promoted azide alkyne cycloaddition. Since this was like the idea behind it was that the strain itself is, since the molecule or compound is under so much strain, it's kind of gonna, instead of going like this, like being really strained together, since I'm trying to put a visual representation, it'll kind of open up and then cyclize, similar to what the 3,2 promoted cycloaddition was. Like the strains on the hydrocarbons, and then it's going to open up and then release that strain. And they found that it was compatible and that it worked smoothly. So in 2012, she released an article that is called Probing the Microbacterial Trehalome with Bioorthogonal Chemistry. And this was published September 14th of 2012. And in this article, it utilizes the metabolic pathways to label glycolipids in mycobacteria with analogs of azide-modified trehalose. So for this one, I remember her also mentioning there was a background. So the disease background for this was tuberculosis. So they were trying to, I believe they were trying to track the pathways that, so they probed the, they had the target molecule, they were able to probe it, and this research was basically tracking the molecule, the biological target molecule, with the molecular probe. So they tracked it, and they were able to find 4 pathways that they didn't know that the biological target compound was taking in the body. So that alone opened up so many doors for further investigation of to why is the molecule taking this pathway instead of that pathway, or what is causing it to go in these 4 separate ways, like taking 4 different routes instead of just sticking to the same route in the body. So a couple years later, she published an article called The Site-Specific Antibody Drug Conjugates. And this kind of just went into protein engineering and drug development. And the purpose of this article was to see if they were able to place or put multiple like attack an antibody on multiple positions. So at the end of the research, they discovered that using the bioorthogonal chemistry, it enabled them to be able to covalently append a drug molecule and to various sites on the antibody specifically. So the bioorthogonal chemistry opened this door to use for antibody drug conjugates. So then a year later, in 2015, she released the systemic fluorescence imaging of a zebrafish glycan with bioorthogonal chemistry. And basically in that article, she incorporated a cyclooctane that was functionalized as sialic acid. And the reason that they were doing that is basically because they wanted to do a reaction of fluorescent tetrazine, and to see if that would allow them to get basically better imaging of what was going on with the cell itself and the zebrafish glycans. So what they found after conducting the researches was that using the bioorthogonal chemistry method and pathway, they were able to view imagings of the ciliated glycoconjugates that lived in the zebrafish embryos. So throughout her career, she's done other work, not just focused on bioorthogonal chemistry. That was just what interested me, because I thought it was really cool that she found something that she knew could help her and that she would be able to utilize in her research. And when they determined that it wasn't, not that it wouldn't be useful, but that the way that it was at that moment wasn't going to be useful, which was the copper catalyzed. The copper catalyzed method. So that was with and then we have our plus here and our minus here. And we also have, can you see that? Yeah. We also have this group with our molecular probe. When these reacted together, it closed in itself and it made a cycle with the nitrogens in it that looked like this. I'll draw it up. So when these two reacted together, and I'll draw this like that, and then we have carbons here, and let me get the other one. We have our double bond here, and we have a double bond here, and then we also have the biological target and the probe. So we're going to attach the probe on there as well. So it was interesting to me that she was able to see something that she knew would be beneficial to her in the future, but just not at the moment. And what she did was just re-innovate it. So like how this was the copper catalyzed one. Well, she okay. We can stop. So how this was the copper catalyzed one, how she just noticed that yes, this reaction does happen quick and efficiently, and it is a very high yield and little to no waste. It doesn't work in my area of research in what she likes to do, which is studying diseases and more of the biological side of research. So I enjoyed that she went and like put herself out there and kind of was like, well, I understand the concept behind it, but now I'm going to make it work for me, which is when she started incorporating the Schrodinger ligation and the reduction, and then as well as the ketones and the aldehydes, and also like I mentioned previously, she's starting to, or in the past, she was introducing the quadracyclane type of reactions that was new to her as well. So I like that she just kind of knew that she had something to work with, and even though it didn't work for her in that moment, she re-innovated it into something that was really beneficial for the entire world in the medicinal sense and pharmaceutical, as well as research and development. And my reason behind saying that is because her most recent article that deals with the bioorthogonal chemistry still kind of shows the growth of her research. So her recent article puts into perspective how ahead of her time she was thinking. So her recent article is called Bioorthogonal Labeling of Human Prostate Cancer Tissue Cell Slice Cultures for Glycoproteomics. And this was basically the goal of the bioorthogonal chemistry in the first place, is to be able to say, this is my target molecule, I want to probe it and follow it. And now in her recent article, she's showing that using bioorthogonal labeling, so being able to label your target molecule, you can then watch it in the system or in its environment without harming the cell that you targeted or probed, and without affecting its way that it would normally take, like its normal pathway. And in this case, it worked well for her because she had already been doing research on cancers as well as tuberculosis, and she was kind of surrounded in wanting to know reasons behind diseases. And it was just interesting that she was able to see something that didn't work for her and turn it to another, like on a different way, and end up like creating something that changed the world. So in the article that I just mentioned, it was mainly focused on getting a better understanding of specific glycoproteins that contribute to cancer. So the first application of the glycoproteomic platform to human tissue cultures was like outside of the body. Like it was still a live cell, but it just was outside of the body because they wanted to just see what would happen first. And they did that with normal They did that with normal prostate tissues that were sliced, and they also did that with cancerous prostate tissues and cultures. In what they did was added the azid functionalized salicylic acid that I mentioned previously in one of her past articles with the zebrafish glycan. So they took a similar method with the azid the azid functionalized salicylic acid part to be pushing the reaction and to be. So what they were able to find was that glycoproteins that are uniquely found in cancerous tissues were at an elevated level, and they were able to identify it because they targeted the molecule. They were able to use the bioorthogonal chemistry to target the molecule and then track the molecule's pathway because they probed it and were able to later then visualize it due to the fluorescence occurring around the molecule itself. And that was her most recent article that revolved around there. So if you're interested in doing a little bit more research or wanting to get a deeper dive onto it and not just kind of like an overview of her generalized research, she has published various books and various articles. So some of them are called, one that I read was called A Decade of Bioorthogonal Chemistry, and it was published in the Accounts of Chemical Research in 2012, and that it's a short article. It's probably like 2 pages, I believe, and it just goes over the main findings, the main, so they're like, their approach going into it, what they found, and that aspect over the 10 years of them trying to perfect and work with and add new additions and reactions to the bioorthogonal chemistry like reaction set that had already been made. Another one that she has had published is called Imaging Cell Surface Glycans in Animals with Bioorthogonal Chemistry. And in that one, a lot of her research is done on living animals or living animals' tissues, so mice or zebrafish, or even sometimes like she'll do ovarian cancer cells and just like tracking those. So the article that I just mentioned that was published in 2014, it was published in the Glycoscience Biology and Medicine journal, and it's on pages 764 to 768, and there she just goes into or like touches on the principles of like behind the imaging cell surface glycans and the principles around the bioorthogonal chemistry, and she also goes into some of the key mechanisms. So I also read that to like touch on like the Schrodinger ligation as well as the copper catalyzed. So there was a few articles that kind of I just mushed together that was able to help me like understand the mechanisms and reaction of what was actually going on in a chemistry sense. And the last article I'm going to mention today is called Design Strategies for Bioorthogonal Smart Probes. It was published, it's one of her more recently published articles that goes over and kind of does the overview of the bioorthogonal chemistry. And this one specifically is going into the probes or the smart probes that are used to push the reaction. It was published in 2014, and it gives more information on some of the reactions that I mentioned, like the ketone reaction. And the ketone reaction is similar to the aldehyde. So the aldehyde and ketone are kind of, they work in the same way. And that one is like a nucleophilic condensation. And then she also introduces new ones that I hadn't mentioned that were found as the research was continuing, like an nitrilamine acyclo addition. So she mentions that as well as alkene. It's alkene acyclo addition. So a nitrilamine alkene acyclo addition, as well as a tetrazine ligation, which that one was touched on, I believe, in one of the articles that I mentioned. I don't recall if it was the zebrafish one. I think it was the zebrafish one where they used fluorinated tetrazine. So in the zebrafish one, so she's kind of touching on that. So if you want to have another article to reference, I would recommend the zebrafish one because that's where she uses the tetrazine ligation part in there. And then she also just goes over more interesting bioorthogonal reactions, or what I thought was interesting. So yeah, that is Carolyn Bertozowski. Bertozowski. Okay, girl, be quiet if you can't pronounce her name. So yeah, that is Carolyn Bertozzi. I had a great time researching her. I enjoyed that she is a woman in STEM, and she just was able to reinvent something that she saw wasn't working, that she liked. She reinvented it to go to work for what she wanted to do and find a passion, and just like gathered a whole group of people and just created this new realm of science. And it was really cool researching her. So thank you for watching. Bye.